So going on to discuss our fourth factor that affects the rate of reaction, temperature. So it turns out that just about all reactions will happen faster at higher temperatures. I like to think about the fact that I wash my dishes under hot water instead of cold. Why? Because that hot water will increase the motion of those particles, the food particles on my plates and my pots and pans, and get them off of my dishes faster than if I were to be washing them in cold water. So let's examine that a little bit further. So when I increase the temperature of a system, then that's going to cause those reactant molecules to move a little bit more quickly. They're going to move more rapidly, and if they move more rapidly, then they're going to collide with increasing frequency. So, well, why is that? Well, when I add thermal energy into a system, that thermal energy transfers to the molecules of that system in the form of kinetic energy, and that kinetic energy is going to cause them to move around more rapidly because, of course, kinetic energy is the energy of motion. So, again, it all comes down to the likelihood of there being a collision between the particles in a particular reacting system, and in particular the amount of collisions per unit time. So looking at that, examining that just to illustrate it a bit, here on the left I have a vessel filled with particles with lower kinetic energy. Okay, they're going to be cooler, so they have less kinetic energy, remembering, of course, that temperature is just simply a measure of the average kinetic energy of the particles of a substance. And then over here on the right, I have particles moving faster because I've heated them up. I've increased their kinetic energy by transferring thermal energy into the system. Okay, so the final factor affecting reaction rates is whether or not a catalyst is used. I'm not sure that you remember what a catalyst is. I can't recall whether we've discussed this yet in class, but let's go through it from the start anyway. So a catalyst is a substance that you add to reaction to control the rate of the reaction. Usually you're adding a catalyst to increase the rate of a reaction. Okay, so you add it in to speed up the rate of the reaction in most cases. So the thing about catalysts is that they're not actually involved in the reaction, so they're not listed on the reactant side, they're not listed on the product side. Often you'll see them over the reaction arrow, and that's because they're not a reactant or a product. They're actually a recycled item. So they're indirectly involved, but not actually used or produced. So I have a little illustration here to help you make sense of that. So this particular catalyst is a solid catalyst, some sort of a metal, and you can sort of think of it as a landing dock. And there's something about it and its chemical properties that allows the reaction to happen between two other molecules happen a little bit more readily. So for instance, I have this green molecule here and a yellow molecule here, and each of them, they want to react, but maybe under normal circumstances, without the use of a catalyst, there's insufficient energy for that to happen. So we see here that in step 1, this green molecule is landing on the surface of the catalyst, and in doing so, that somehow changes the amount of energy needed for the reaction to happen. Then in the second step, we see this yellow molecule landing and bonding, forming some sort of an intermediate species here with the green molecule. And then while on the catalyst is affecting the amount of energy needed for that reaction to happen. And so then we can see that the bonds between our green diatomic molecule and our yellow diatomic molecule are able to be split. And then once that happens, they happily leave the surface of our catalyst, and our catalyst remains there, able to be used again and again and again by other green and yellow reactant molecules. So the most practical example that I can think of that you can relate to is enzymes. So in biology we discuss biological catalysts, and the name for that is the enzymes. And so there are lots and lots of reactions that happen in living organisms that require enzymes. One that sticks out for me is cellular respiration. Without enzymes, cellular respiration and life as we know it would not exist. So enzymes are super, super important. We probably discussed this last year, though I'm not sure if you remember. In our saliva, there are a couple of different enzymes, but the one that sticks out to me is amylase. And amylase, its job is to start breaking down food right in our mouth, right in our oral cavity, before it even moves down into our stomach. So the job of amylase is to take longer, more complex carbohydrates, like starch, I would say, which is essentially just a long chain of glucose molecules, and to break it down. So here we have carbohydrates. So carbohydrates is a general name for an enzyme that breaks down sugars. That A's ending is your giveaway. But amylase specifically is the sugar that's is a enzyme that's going to break down starch into disaccharides. So in here we see just individual sugar molecules, but the point remains the same, which is that without our amylase or our carbohydrates, we would not be able to start digestion in our mouth, breaking down complex carbohydrates into simpler sugar molecules. All right, so our next topic is collision theory. So collision theory is a theory that discusses basically how reactions happen at the molecular level. So collision theory also states that the rate of a reaction is basically dependent on how many collisions occur between reactant molecules or atoms, successful ones that is. And so we're going to talk about what it means for a reaction to be successful. So in this first example, I have a red molecule and a green molecule that are coming into contact, they're colliding. But for whatever reason, there's no reaction that happens. They both leave unchanged. And so that we would classify, I'm going to stop this because you can't read it. Let's try that again. So that we would classify as an unsuccessful collision. Whereas in case B here, I see the orange and the green molecule approaching each other. Some kind of a bond breaking and bonds forming happens, and we see that new and different products emerge from that reaction. So that is in chemistry what we call a successful collision. So a collision that's successful is one where the reactants are changed as a result of the interaction. So essentially there are two basic requirements in order for a reaction to be successful, in order for the collision to be successful. And the first is that the reactant molecules or atoms have to collide with enough kinetic energy. If they don't have enough kinetic energy, then they won't be able to have enough bond association energy to break the bonds that need to be broken. And the second thing is that the reactants must collide with an appropriate orientation. In order for the molecules, or the atoms on the molecules rather, that need to be exchanged to be able to make that exchange, they have to be positioned sort of next to each other. And I'm going to elaborate on that. So in my first example here, so I can see an unsuccessful collision on the left. I see that, I have this black and red molecule here colliding with this blue and red molecule, and I can see that the red ends are next to each other. They're colliding. And then they're rebounding unchanged. Well, in this case, the explanation for that is that, in order for these two molecules to be able to collide successfully, they need to be oriented differently than it's showing in this diagram. So let's look at example B. So here's another example of what seems to be an incorrect orientation. It seems that, the black and red molecule does not want to collide successfully with our blue and red molecule if the red end of the black one is oriented right next to the blue atom in the molecule on the right. So they're going to rebound, and again, that's an unsuccessful collision, and they rebound unchanged. Okay, so our next example is one where we see the reactant molecules oriented such that the black end of the red and black molecule is next to the red end of the blue and red molecule. Okay, and so they collide with the correct orientation and presumably enough energy as well. And what we have in between, before our final products get made, we have this thing that exists, this species that exists, that while bonds are both being formed and broken. And that's called the activated complex. And it doesn't really exist for any real time. It's just sort of there in the middle of, reactant and products. But it doesn't last any measurable amount of time. So that's called the activated complex, and it's extremely unstable. Okay, and then we see our products formed. Now, the last and final case is one where they might be oriented right, okay, but for whatever reason, when they collide, they don't have enough energy. There's not enough energy in the system to break the required bonds, and so they rebound unchanged. So there are 4 different cases where we've seen some successful and unsuccessful collisions based on different reasonings. Now, next is a really, really important concept. Think about a rubber ball hitting a wall. Okay, so the rubber ball, in order to hit that wall, it's going to have to approach the wall, and whether or not we think about it, when it hits the wall, it has to stop, and then it has to change direction. Okay, well, the same thing is true of 2 atoms or molecules meeting during a collision. They have to slow down to meet, to stop, so that they can change directions in the rebound. So in order to slow down, they must therefore reduce their kinetic energy. But the thing is that kinetic energy has to go somewhere. It can't just kind of evaporate. The kinetic energy has to be transformed into some other kind. And what happens with the molecules when they reduce their kinetic energy is they store it. They store it by converting it into chemical potential energy stored in the bonds. So what that does is it increases the total potential energy of the molecule. And here is a nice graph to show this. And we're going to be looking at a lot of graphs that look like this. So let's take a good look at the axes. So on my vertical axis, I can see potential energy, and that's in kilojoules. And on my x-axis, my horizontal axis, I can see the reaction progressing. And so at the beginning, at point A, there I have my reactant species. So the reaction has not happened yet. Okay, so the molecules have not yet collided. Okay, so when molecules collide during the collision, again, remember the kinetic energy has to go down so they can slow down. But that means that my potential energy has to increase. And so I can tell right here that the reaction has happened because I take my reactants, I reduce their kinetic energy when they slow down, but that transforms quickly into potential energy during the reaction. And then as the molecules rebound, they speed up again, and that decreases my potential energy because in speeding up, they regain the kinetic energy that they lost.